Hello, welcome to Weatherwise. I'm meteorologist Nathan Scott. In this week's segment, we're going to be talking about severe weather forecasting. We'll start off with the synoptic features, or the big features that lead to the potential severe weather here in the United States. And then we'll focus on more of the smaller scale features like the low level jet and the parameters. Finally, we'll wrap things up with the all-important information that comes from the skew-T diagram. When we talk about severe weather forecasting, things have really changed over the past 10 to 20 years. Before, we made no mention that we were going to have severe weather 6, 7, 8 days out. And that's just because the Storm Prediction Center did not have any outlooks until 2007 when they did release them officially, and anybody can get that information. And that's why you're hearing more and more when we're looking long range forecasts that there is potential we could see severe weather 8, 9, 10 days down the road. But it's also because our weather models are much more advanced and sophisticated. We recognize the pattern that can lead to the potential of severe weather. So for example, here's 11-day forecast. This did not used to be a thing. Remember in the 90s, you pretty much had a 5-day forecast. Then it was a 7-day forecast. And now we've got 10-day, 11-day, even 14-day forecasts in some cities across America. And once again, that's just because our confidence has gone up since weather models have become more and more advanced. However, the farther that you get down the road with your 10, 11-day forecast, your confidence goes down as a meteorologist if it's a very active weather pattern. If it's a stagnant weather pattern and we just have an area of high pressure or a heat dome over the region for the next 10, 11 days, that's a very easy forecast to look over. Let's talk about what's happening out there for necessarily this week. We do have the potential of severe weather for Northeast Arkansas in this case, and this is a 5-day outlook issued by the Storm Prediction Center. So once again, how did they come up with this in the first place? Well, we have to take a look at what's happening across the globe. There's always waves making their way across the globe, and that's just because air is a fluid, so it operates in fluid dynamics, and you see this wave feature over the United States. But when we look upstream, say because everything moves from west to east here in the northern hemisphere, you see these waves. So this wave eventually in China will reach us in America. It may take 2 or 3 weeks to get here, but that will have an impact. And anytime throughout the months, there's going to be 4, 5, 6, maybe 7 or 8 of these waves moving across the globe. That wave into Europe, which may have affected us just about a week ago. It will continue to cycle its way around the globe and will eventually impact us here probably in another month or 2. This is just an example. This is not exactly what the atmosphere looks like at this time. When we take a look at the wave features, that's what's important, because the ups and downs will tell us the story, what's happening in the upper parts of the atmosphere, and then what could happen down at the surface, because it's all related. So when you have a ridge or a feature that goes like this with the wave pattern, that's known as a upper level high pressure or as a ridge. And this is an area of sinking air and compressing air. Compressing air is warming air. So in the middle of summer, you get these domes of heat that build across the deep south, the southern plains. And those domes of heat usually lead to hot temperatures, and they suppress any chance of really organized activity of shower and thunderstorms from bubbling up because you have a lid on the atmosphere. These also block any big significant storm systems that try to make their way across the country. They hit that wall, you see where it says here, blocking wall, and that basically can lead to the potential of drought developing if this heat dome sticks around for too long. On the other side, we have what's known as an upper level low or a trough. And under this area, you have rising air, especially to the right of the trough axis. And we're going to talk about more on the trough axis and the orientation of that, because that plays a very critical part in severe weather. Cooler temperatures and also rain and storms are likely when you are underneath a trough of low pressure. Let's take a look at this example. We got a trough off to the west, and we have an area of high pressure to the east. So you got the battle zones on what's happening in the center part of the country. And when that happens, especially spring, you're going to most likely have an area of where there's going to be thunderstorms that develop and maybe the potential of severe weather. And that's just because an upper level low eventually will develop a surface low. And that surface low will continue to develop, strengthen, wind up, and bring in a lot of warm, moist air from the Gulf. Meanwhile, it's colliding with that high pressure off to the east. So that's the setup that we typically see here with potential severe weather in Arkansas. I told you about the trough axis. So when we have a trough that looks like this, you see the trough axis is oriented from the northwest down to the southeast. This is known as a negative trough axis. And meteorologists are always looking at weather models and current data information to see how the orientation of the trough is. When you have a negative trough axis, this is an area of rising air and a lot of warm air building into the region. So that increases the chance of severe weather, especially to the right and along that trough axis. On the other side, you have a positive trough axis. So you see the orientation of the trough axis goes from the northeast down to the southwest. So rising air is not as pronounced in this area, and your chance of severe weather is lower, but certainly cannot be ruled out. You can still get severe weather with a positive tilt trough axis. I told you how this is all related when it comes to what's happening in the upper parts of the atmosphere versus what's happening at the surface. It all comes in cycles. So now we're going to focus on the surface a little bit. We have an area of low pressure in this example developing into Kansas. You have the cold front draped across Oklahoma and Texas, probably a dry line as well. And then to the east of the cold front, you've got a surge of a lot of warm air, very warm and humid air, because the winds are coming in from the south as airflow around the low pressure counterclockwise, so that's bringing in all that unstable air right across Arkansas and the deep south in this case. And there's the warm front. So in between the warm front and the cold front is known as the warm sector. And when you have a low pressure, especially wintertime or the springtime, and you're in that warm sector, that could be a trouble area of where severe weather could certainly develop. As the low pressure develops, not only at the surface, but also in the mid-levels of the atmosphere, it will develop a low-level jet. So there you see the mid-level trough. In this case, it's negatively tilted, and we have the jet stream that's making its way right across Arkansas, Mississippi, and also Tennessee in this example. Within the jet stream, there's actually a core of higher winds. So with this example, we have the highest core winds right over central Arkansas, right over Little Rock, and you see it goes from 30 to 50 to 70 miles per hour. Examining this core and actually cutting it up into different sections will tell us another story on where severe weather potential could exist. So with this jet streak, when we divide it into 4 regions, we have the right exit, the right entrance, the left entrance, and the left exit. And that's just because as a bubble of air or a parcel of air moves from Texas into Arkansas, it's going to encounter different conditions. And these different conditions allow meteorologists to figure out where there's going to be rising air within this sector of the jet streak versus where there's going to be sinking air. So when we break this down even more, you see at the bottom panel right there, the right entrance and the left exit regions are going to be the regions that have a higher chance in producing severe weather and a higher chance in rising air, and air that could lead to severe weather potential. So those are really the synoptic features that we break down when it comes to severe weather forecasting. Coming up next, we'll take a look at CAPE and other parameters that meteorologists are always looking at as the event gets closer and closer. Those numbers and that information will give us a better idea on how serious severe weather could be. Stay tuned. Storm fuel. We always talk about it here on THV 11, and that's just an indication on how high the storms can grow for the most part. The more storm fuel you have in place, the likelihood a storm can go 40, 50,000 feet into the atmosphere, and the higher the storm cloud is, the more powerful updraft it will develop, and that could lead to the potential of severe weather. So in this example, we're looking ahead, and we've got lots of storm fuel for this case, which is actually happening for this upcoming Friday on, I believe it's going to be May 16th for this case. So we have a lot of storm fuel in place, especially over Oklahoma. We've got lots of storm fuel across southwest Arkansas and even into northeast Arkansas. We can have as much storm fuel as possible, but if we don't have anything for the air to rise, then this doesn't mean anything at all. You can have storm fuel that goes into the 4,000, 5,000 joules per kilogram, but if there's nothing to initiate a storm, then it's just pretty much there and won't be used at all. Let's take a look at this case, though. When we look at the upcoming model information with this, we are looking at the potential of storms developing. This is the European, and we do have storms popping up where this green is showing. So not everywhere where the green is showing there's going to be rain, because obviously we're so far out. We're about 4 or 5 days away. This will change, but this definitely gives us an idea on we do have the potential of storms. And with that storm fuel in place, let's look at something else. Let's look at the winds, because the winds tell us the story on if we have any shear in the atmosphere. So when you have a lot of CAPE available and there's not shear, you're going to have a hail event or a downburst event when you have the winds that just collapse from the storm cloud and then just make their way across the ground. That can produce winds 70, 80, sometimes over 100 miles per hour in some cases. But for a storm to have wind shear, it's going to tilt, and that's going to allow the updraft to last for a longer period of time. So here's the surface winds according to this example. Once again, this is May 16th, and we've got the surface winds coming in from the south. When we take a look at the winds about 850 millibars, and we do say millibars because we use the metric system in science, of course, but this would be about 5,000 feet above the surface. We've got the winds, and you notice how fast they're coming across from the southwest to the northeast. So with this, we have shear that is trying to develop into especially east central Arkansas and also parts of northeast Arkansas. And I showed you earlier with that slight risk, that's why they have issued that slight risk in advance so far with this case that's coming up, because that's where they're saying all the ingredients are coming together for the best shear, and also you have storm fuel available as well. Let's go over Storm Track 11 now. We're going to take a look at one weather model. This is the GFS. But as a meteorologist, it's not just the shear, it's not just the winds at 850 millibars we're looking at. We've got other information we have to look at, because, of course, the atmosphere you have to think about, even though you're looking at two-dimensional graphics, you have to think about what's happening in the 3D realm of the atmosphere. So we have the 850 jet here, and remember what I told you about how the left exit, right entrance, those all work out. So we're looking at the right entrance, left exit of this jet at this time. So if there was potential severe weather, it's going to be right here, because you see the winds are picking up from 40 knots to 45, and then we get into the core here, 50. So this is going to be the area of, in this case, where severe weather potential could be located, which also matches with that slight risk potential. Now let's take a look at maybe some winds at 500 millibars above the surface. So now we're getting about 15, 20,000 feet, 25,000 feet above the ground. And we don't have anything too significant, but there's definitely some wind energy there. Now I'm going to break it down to severe weather criteria. So we are looking at a lot of information when we're trying to come up with a forecast for you at home. It's not just, hey, this is what the Storm Prediction Center says. No, you have to look at each individual information of all these different parameters that will give you the confidence on if severe weather is possible, if it's changing, if it's increasing, decreasing, and also is where the location that it was expected to be has shifted, because maybe the 850 jet has shifted according to different model information. So here is the surface base CAPE, and there you see this is Saturday, 0Z, so this is 8 o'clock Friday evening, and we have quite a bit of CAPE. You got numbers like that showing up, 3,000. That's some big time CAPE to work with. So these are going to be some really tall storms if they do initiate. Let's see if we have any what's known as SIN, and that is basically how we describe a lid on the atmosphere. And we really don't have a lid across central Arkansas, but there is some SIN into northeast Arkansas. Now we're going to look at what's known as the Energy Helicity Index. And this basically says on how things could maybe rotate, the chance of rotation going into this event. And it has picked up here where this red is. So the storms that develop in that part of the area will have a higher chance of rotating. Along with that, the supercell composite. Again, it's going to be where supercells or rotating thunderstorms are expected to be. And it looks like, for this example, on May 16th, the chance, according to the GFS, is looking like northeast Arkansas, northwest Tennessee, getting into the boot heel of Missouri. Let's take a look at the hodograph just for fun. So hodographs, this is going to get a little more confusing now. We're going to get to skew T in just 1 second, but what we're looking at are these U shapes here. So when we have U shapes within these hodographs, that gives us an idea of also where shear is located. If storms develop, you have a curved hodograph in that location, then you've got the potential of dealing with storms that could rotate and become supercells. We're going to get more into skew T's coming up right after the break. Stay tuned. In an earlier episode of WeatherWise, I sat down, talked with the National Weather Service meteorologist all about upper air observations, weather balloons. And that's just because weather balloons are very critical in finding out what the atmosphere is actually producing. We launch weather balloons all across the country twice a day. In this case, it's 8 o'clock in the morning, Central Daylight Time, and 8 o'clock in the evening, Central Daylight Time. And that gives us an idea what's happening not only at the surface, but we get a vertical profile of the atmosphere. Temperature, dew point, also winds from the surface way up above us. So let's take a look at one example here. This was the weather observation from the weather balloon that was launched this morning, which would have been May 12th. And you see a lot of lines here. So when you look at this, you're looking at this red line. This red line is the temperature profile. So at the surface, we were at 61 degrees, and then these dashed lines right here are the temperature, of course, decreasing as you go more to the left of the screen, and then they increase the more right that you are from that temperature line. And it is in Celsius. So 0 degrees, of course, is 32 in Fahrenheit. 10 degrees is going to be 50 in Fahrenheit. 20 degrees is going to be 68 in Fahrenheit, and then 30 is 86 in Fahrenheit. Follow this red line, and you can see the temperature, of course, decreases with height. No surprise. Although, right here, just below the 700 millibar line, we actually have an increase in temperature. And when you have an increase in temperature, that's known as an inversion. An inversion can stifle storm development and can be a lid to storm development in certain cases. The green line is the dew point. And when you have the red and green line pretty much on top of one another, that means you have 100% saturation. So right at the bottom here, you see the dew point's at 60, the temperature was 61, therefore there's some fog developing probably in some parts of the region because we had almost full saturation right at the ground. And you'll see this according to what type of clouds you're seeing. If we have those stratocumulus clouds, the air temperature and the dew point will be very close together, and it may just be about 900 millibars off the ground. Looking over to the right, we have these wind barbs. You follow my cursor here, and that tells you the direction of the wind, and it also tells you how strong the wind is in knots. So this one right here is a 10-knot wind from the northeast, and then we continue to have a 10-knot wind. It's going more north-northeast, and then as we go up, it shifts more to an easterly direction. We got a 25-knot wind, looks like about 700 millibars, or excuse me, about 600 millibars, but nothing too crazy. Let's look at an example with a significant weather event that unfolded here in Little Rock in just 1 second. Because along with this skew-T, yes, we have the air temperature and the dew point, there's so much more information that we're looking at. We've got CAPE, which is down here in the chart, if you follow my cursor. Surface CAPE 24, that's pretty weak. No CAPE there really. Your SIN, minus 40, so obviously in this case we're not going to have any storms because we don't have much CAPE. You got to have CAPE about 500 to have storms for the most part. I'm not going to get into every parameter, but this is just a lot we're looking at. The precipitable water, 1.24, the downdraft CAPE or the DAPE. Then we have convective temperature. So the convective temperature right here, if it was sunny and there was nothing else to initiate any storms, but we hit 74, those clouds would grow. You would see those fair weather cumulus clouds start to grow into cumulus congestus. And then we have the hodograph, which looks pretty pathetic. So basically, we were looking at the center, and you're thinking about, again, 3D level here, 3D imagery. You launch a weather balloon, it goes up into the sky, and this is kind of the path that it followed. There wasn't too much wind, so it went from east to west because of that easterly wind, and it didn't get too far away from the actual launch site, it looks like. Now we're going to switch things over to this event, and I'll let you know what this is in just 1 second. You probably can see it there if you're cheating, but this is the morning, and we have an inversion right there. Okay. The CAPE is not too strong. Let's look at the hodograph. The hodograph is very curved. And this is because look at the winds that we're seeing with this case. The winds greatly increased. We had a 50-knot wind on this day that was just about 3,000 feet above the ground. And then those winds continued to increase. So the winds from the surface went from the south and then turned over to the southwest and eventually the west as you got higher and higher into the sky. This is something that's very concerning to a meteorologist looking at this hodograph because it is a curved hodograph. Even though right now it doesn't look like much because your CAPE is at 3, this inversion is going to disappear as the temperature warms from 67 to much more significant. So let's go look at that again at 21Z. If this is going to work for me. Okay, so this is 21Z. Let's go 0Z because I don't think that's Shreveport. So this is 0Z. And here we go. Look what's been going on here. Look at the CAPE. The CAPE has come up 1549, and that CAPE is calculated because you go from this point here, from the 850 where this red line meets this dashed red line or maroon line, and it goes all the way up here to almost 200 millibars. So this graph tells us how high the cloud can grow. And this is known as the area of CAPE, convective available potential energy. There's the photograph. I'm going to go back a little bit because this was a unique case that happened here in Little Rock. And in case you don't see it, it's the March 31st, 2023 case. That was when we had that EF3 tornado go right through Little Rock. And it's just because, look at this photograph, lots of wind shear. You look at the STP, the significant tornado parameter, that was up there in the lower left-hand corner, right-hand corner. So everything was coming together. I mean, look at your winds. That storm was spinning like a top because you have the winds from the south at 30 knots, and then it continued to go up. You got a lot of CAPE available, and it was just really, one or two storms that went wild, but this is the type of environment that a meteorologist would say, uh-oh, for the most part. We'll get more into SCU-Ts coming up in later episodes. There's so much to talk about with the SCU-T and upper air weather observations from weather balloons. Weather balloons are very important to the field of meteorology, and I know some balloons have actually been taken off due to the new ideas from the government. Hopefully, there are going to be replacements for the balloons that they don't launch anymore, but due to apparently NWS staffing, they've decided to take some weather balloons off the docket for right now. Hopefully that does change, because the more weather observations we have, the better forecasting models will work. Thank you for watching WeatherWise. I'm meteorologist Nathan Scott. If you'd like to shoot me an email, go ahead and do it. It's nscott@thv11.com, or you can also message me on my professional Facebook page. Have a great day, and I'll see you soon.